I'm amazed you've all made it this far. Alright, so it's week 11, almost done. And I think we are pretty much done with C. All the extra, there's no more constructs that you can actually learn about C. Maybe a bit from the C preprocessor, we'll look at that today. But this week is really going to be sort of talking around the process of programming and the various tools that are available to help you. Although I did want to finish off the Q stuff that I started last time, because as I was writing it on the weekend, it took me 3 goes to get it right, which is unusual. Most of the time this semester I've got it right first time, maybe with one minor bug. But Qs are an interesting one, you've got to think a little bit about them. Alright, so Andrew says he's going to do the assignment 1 auto marking today, sometime, after he finishes his lecture. And he reminded you not to delay starting assignment 2, like potentially you delayed starting assignment 1. Oh, that's not relevant. There's a couple of things to help. Last week's lab exercise was something to do with a very simple bot that just got petrol. It's been finished, so there's a solution to that. So if you've really got no idea, take that and start modifying it so that rather than just buying fuel, it buys other stuff as well. And apparently there was an assignment related question or 2 in the tute last week, and he's done the solutions to those, so you might get some more ideas there. And he asked me to remind you to submit every day, or after a session, making some changes, submit. Using Give. Give sticks it into a Git repository, which basically means that you can get backups of it. So if you lose your files, or if you make a whole lot of changes and they screw everything up, you can always back up to the previous version and start again. So Give frequently is a useful idea. We only marked the last one, so you can give as many times as you like. Alright, let me see, where will I start? I might actually jump down to the bottom, because I wanted to talk a little bit about debugging, because I came across a couple of bugs in my code, and the process of finding them reminded me that we haven't talked about debugging so much in the lectures. So, what debugging is all about, you inevitably put errors in your code. You don't try to, but it just happens. You get a bit sloppy, you don't quite think while you're typing in one line of C code, and that screws everything up. So debugging is all about finding the bugs and then fixing them. A lot of people think fixing them is the hard bit, but it's not. It's actually finding them in the first place. So once you find the piece of code that's doing the wrong thing, working out what it's supposed to do, and then writing some C code to do that is generally pretty straightforward. But when you first start with your program, there are a number of things that can go wrong. You can start the program running, and it runs for a long time, and you think, maybe that's just a lot of recursion, and you wait longer and longer and longer, and nothing ever happens, and you realise that it's never going to terminate. So you can get into an infinite loop. Working out where that is an interesting question. We'll look about how to deal with that with the debugger in a minute. If you're lucky, I would argue this is the luckiest case of all, the program crashes and you get a segmentation fault or something like that, and maybe, I'm not sure what happens on our machines these days, but you might get a core dump as well, which is basically a dump of the state of the memory when the program crashed, and that contains some extremely useful information. And if you run the program in a debugger and it crashes, the debugger will tell you exactly where it went wrong. So that's an easy case to handle. The case where the program produces incorrect output is not too difficult to deal with. It requires a little bit of thought. The case where the program crashes, you just go to the debugger, look what the state is, and you'll probably find some variable that has a ridiculous value, so you'll know what went wrong. When you've got incorrect output, then you've got to think a little bit about what output was I expecting. All right, this is what I got. Can I think of a reason why this output might have been produced rather than this output? And then you go back to the code and you look through and you can see, oh, the output I got was half of what I expected. Oops, I forgot to put 2 times in the code or something like that. So incorrect output is okay to deal with. Bit of thought required though. And the worst case is a program that runs and produces output that looks all right. It might be incorrect, but if you don't know what you're expecting to get, then you might miss the fact that the output's incorrect. Or even worse, it produces the correct output and you think, all right, that's good. Run another couple of test cases, works for all of them. Good, must be correct. And then you run it, or one of your friends runs it on a different case and it crashes. Okay? So those ones are potentially tricky to track down because the program's going to run. At least if it crashes, then you'll know you can back to point 2. But you can get fooled into thinking your program's correct just because it handles a few test cases. Alright, so basically every error in a program is caused by a mismatch between what you thought you were writing in the code and what you actually wrote. So I intended to write something to multiply by 2, but I wasn't paying attention and I accidentally multiplied by 3. I mean, that's a trivial kind of example, but it's that kind of thing that causes the problem. So to do debugging, really what you've got to do, you've got to find out what the program is doing, and in particular you've got to find out, in a large program, you've got to find the precise piece of code that's doing the wrong thing and think about, all right, this, say you're dealing with a function, the function's returning an incorrect value. What was this function supposed to return? How is it computing the return value? And then going and look at what the code actually does and seeing where the mismatch is. Critical to this is to find out exactly what the program's doing, and that basically means tracing the values of variables. And one easy way to do that is just to stick in some printf statements. I say that's an easy way to do it, but it has the annoying side effect that sometimes when you add printf statements to the code, the bug goes away. Because you've rearranged what's happening in memory and you just happen to have moved some global object out of the way of getting smashed by a bad piece of code. So printfs actually modify the program, so potentially you're not exactly looking at the same program anymore while you're trying to debug. So, you know, this is kind of Heisenberg. When you start observing things, they behave differently. So when you start observing with printf, you're looking at a different version of the program that originally crashed. So that's potentially a problem. So if you want to keep looking at the same version of the program, then you need a tool to help you, and debuggers are the things that do that. So basically what a debugger is, it's some kind of program that controls the execution of some other program. And what it can do, you can start the program running and then you can stop it at a certain point. If you set a breakpoint, we go into this function, I stop the program running. And then you can look at the current program state, you can look at what are the parameters to the function, what are the local variables, and you can step through the code one statement at a time and keep looking at the variables and see how they're changing, and eventually you're going to spot where it's doing the wrong thing. So debuggers provide, you know, a fairly small set of operations, but they're extremely useful. The standard debugger on Linux is GDB. And I left out something that's important. So when you're compiling and you want to use the debugger, you need to compile with the -G flag. So here I've got an example. I've got a program that's produced from 2 source code files, you know, maybe one's a stack library or something, and the main program, and we produce an executable file called myprog. We then run it and it crashes. We can then use GDB to run the program again, run the same program again, and try and work out what went wrong. Alright, so that's enough about debugging. So let's take a look at the queue example from last time. So I'll open up the queue library. Where is it? So we just started, I think, implementing queues as arrays. Now remember what a queue is: first in, first out data structure. The first thing you add to the queue is the first thing that comes out when you do. So enqueue adds it to the queue, dequeue takes out the thing that was added longest to go, the element that's been waiting in the queue longest. Alright, so our queue data structure has an array of elements. They're the things that are being added to and removed from the queue. And we've got a number of variables that tell us where's the first element in the queue, where's the last element in the queue, and how large is the queue currently. And if you want to look at some examples of what that data structure might look like while the program's executing, so here's first, last, and size. Somehow we've got to this state here where we've added 7, 3, and 4 into the queue. This is what we're going to observe. Since 7 appears to be the thing at the head of the queue, the first element, the index of the first element is 0, and the index of the last element is 2. Okay, so I've indicated first and last by red and green. And the size of the queue is 3. Okay, you might say, big deal, I could have worked that out by saying 2 minus 0 plus 1. That's true, but it gets a little bit trickier when things wrap around. So remember, this is an array that's indexed in a circular manner. The index goes through, and when you hit the end, you go back to the start. So you're not necessarily going to have the case that the first item comes before the last item in the queue. It might actually eventually be reversed. Right, anyway, so if we add another item onto the queue, they always go at the end. So 5 goes into that location there. That becomes the new last element in the queue. The first didn't change, but the size of the queue did. So we incremented last, we incremented size. So that's the new state of the queue. If we then do a dequeue, we're going to remove the item that was at the head of the queue, and the size of the queue will obviously go down by 1. We've taken an element out. The first index, the index of the first item in the queue, obviously moves along by 1 because we're no longer considering 7 to be part of the queue. So this is the new head of the queue, and that's the tail of the queue, which hasn't changed. And we can see 7 comes out and gets used somewhere in the program. If we then dequeue another item, so we're going to take the one at the head of the queue, which is 3. The size of the queue reduces again down to 2. The head of the queue moves along by 1 position, so that becomes the new head of the queue. Tail of the queue is still there. Alright, if we want to enqueue something, we need to add it after the tail item. Well, the tail item is at the end of the array, so therefore, since I said this is a circular array, we go back to the start and we add the new item to the tail of the queue, but it's now at the start. Yeah. Alright, so first doesn't change, last does change, and it becomes equal to 0, whereas before it was equal to 3, and the size of the queue is increased by 1. So red shows where the head of the queue is, green shows where the tail of the queue is. And now you can see that the head is in front of the tail. Alright, so if we do a dequeue, we remove 4, that leaves the queue, we advance the head pointer, so we've got one, and we've got one less item in the queue, so size drops by 2, first increases by 1, or at least it advances by 1, potentially wrapping around. In this case, it doesn't wrap around, so the head of the queue now becomes 5. Right, if we enqueue, it adds something at the end of the queue, at the tail. The tail is currently 6, so we increment the tail index, add the new item there. The size of the queue is increased by 1, and the position of the last item is 1 more than it was before. So that increases by 1 as well. Alright, if we dequeue, we take 5 out of the queue, we advance the tail pointer. It was already at the end, so it wraps around, and that becomes the new head of the queue. The new tail of the queue. 9 is still the head of... is that right? No. Sorry, 6 is now the head of the queue. 5 was the head. So the head of the queue is now at position 0. Last didn't change because dequeue doesn't affect the tail, and the size obviously has gone down by 1. If we dequeue again, then we take out... Did I take out the wrong thing? No, I didn't. No, I didn't. That's okay. Alright, so I take out 6 because it's at the head of the queue and it gets removed. The head of the queue moves to the next item. That also happens to be the tail of the queue, and the size of the queue is equal to 1. Right? So we'll stop at that point there. If I did another dequeue, what do you suppose is going to happen? If I do another dequeue, then I'm going to take 9 out, and the size of the queue is going to be 0. And when I've got a 0 size queue, it's also the case that first and last are both pointing to the same index, or both indicating the same index. So in fact, if I did a dequeue here, I probably don't want to change those. I simply want to reduce that to 0. So I'd be left with nothing in the queue, but both of the index pointers pointing at this element here. I guess if you wanted to, you could send them both back to 0. That'd be another option, yeah.
So would the first wouldn't be null? Would we try to dequeue it?
I mean, you could do it that way if you wanted to. That's open to your implementation. I decided you couldn't make it null because these things are indexes, not pointers, but you could have some invalid index value like -1 or something. That's true. Potentially you could do things that way. I just decided I'll leave the indexes where they were and set the size to 0. Alright, so let's go to our code. So that's how the queue is intended to work. Alright, so I've got this fatal function that I had last time, so that just prints a message and quits the program. If something terminal goes wrong, for example, you try to create a new queue object and you can't. So initially we set first and last and size all to point to 0. These two index 0, that one is a counter which happens to have the value 0. So we've malloced a new queue object and we're returning a pointer to that queue object. If we want to free the queue object, we simply go free queue, because all of the memory that we mallocked here is contained inside the struct. So if we go back up here, so all the element, the whole array, and here I've made it very small because I want to show things going wrong. First, last and size, all of the memory associated with the queue is contained in the struct object. So when you want to free up the queue, that's all you've got to get rid of, that struct, which is what that's all about. Oh, what else was interesting here? Oh, the other thing that is potentially not obvious, and I think I did this with the stack as well, that inside queue.h there's a type def that says that a queue type is a pointer to a queue type, QEUE underscore T, that's the convention we've been using. So a queue object, if you like, is really just a pointer to one of these structures. And that's a very common strategy that you're going to use for ADTs in subsequent courses. Having a pointer to some kind of structure, and the structure contains state information about the object. So here the first, last and size are obviously state information. We also happen to have all of the data contained inside this struct as well. More likely what you're going to have a pointer to the first item of data, and that'll point off to other items of data or some other kind of data structure. And typically the actual data won't reside inside this struct, it'll be mallopped in little objects outside the struct. We'll see an example of that when we look at structs, of queues implemented as lists. Alright, anyway, so we've got fatal, we've got queue create, queue free, queue enqueue. Alright, one thing that's clear, we've got a fixed size array, so once the array is full, it's a fatal error to try and add another item to the queue. So we're checking that if the size is equal to max, the array is full, we can't add something else into it, so we generate a fatal error message. Otherwise, if you remember what we're doing, last always is the index of the last thing that was added to the queue. So we want to put, this is different to the stack where the top index was pointing to the next location where you could store something. Potentially you could implement a queue in some manner like that as well. In any case, I've decided that we're going to have last as the index of the last thing that was added to the queue, which it currently is. If I want to add something new, obviously I have to advance that by 1 to the next free location in the queue array, and then here is where I store the item value into that location. And of course, since I'm enqueuing, I need to increase the size. Now there's a number of bugs in this code, but we'll take a look at them in a minute. But you know, if you look at that code and you think about what you're trying to achieve, yeah, right, it looks kind of plausible, but isn't correct. And similarly with dequeuing, right, you can't dequeue from an empty queue, obviously there's no items to take out. Otherwise, we grab the first item from the queue, we decrement the size, obviously we've got one less queue, and we want to move the pointer to the index to the head of the queue along by 1 position. So we increment by 1, and then we return the item that we grabbed from the queue. Now, in fact, this value here is still sitting in the elements array, so we could have just taken it out of that, but I thought it was easier to grab a copy because we're going to do a little bit of fiddling with first sometime in the future. Right, but anyway, once again, at first glance, that looks kind of plausible. Reduce the size of the queue because you're taking something out, and advance the front of the queue to the next item that's going to be removed. Check whether a queue is empty, we just check whether the size is 0. What's the item at the front of the queue? Okay, if the queue is empty, there's nothing at the front, but if it's, that's interesting, that's wrong. If the queue isn't empty, we want to take the elements at the front of the queue. We don't want to take the index of the front of the queue, which is what I've done. What we actually want to do is, didn't even notice that. You see, you can make silly mistakes if you're not thinking while you're typing the code. So I want to take the value, that's the value at the start of the queue, so that's the way I'll do that. So that gives me the front item. How big is the queue? Well, it's already, that value happens to be stored in the structure, so I can just drag it out. And if I want to print the queue, there's some code to do that. So if the size of the queue is empty, we'll worry about this stuff later. If the queue size is 0, then the queue is empty. Otherwise, we can print out all the items in the queue by iterating through size times. So there are size items in the queue, iterate size times. All right. Okay, so let's see how well that works. And I've told you it's buggy, but let's make it works up to date. Okay, so like we had with stacks, we've got some operations on the queue. So plus adds an item to the tail of the queue. Minus takes the element off the front of the queue. It does a dequeue. So plus does an enqueue, minus does a dequeue. You can look at the top element, blah, blah, blah. Actually, that should have recompiled because I changed top. I forgot to save. All right, that's another thing to keep in mind. Make sure that when you're trying to debug the code, you're actually looking at the executable that corresponds to the source code that you've just changed. I've seen people sitting in labs tearing their hair out. One really nasty thing is you've got the code in a number of, you've got the same program in a number of different directories, and you're editing the version in one directory and you're compiling and executing the version in a different directory. And you make all your changes over here and you keep recompiling and the bug never goes away, but you just keep getting the same bug over and over again. So make sure that you don't have that little star up there if you're using gedit. At least that tells you that you haven't saved it. Alright, I won't worry because there are worse things that can go wrong with this program. Oh look, I enqueued 2 and printed out garbage. That's interesting. At least it knows that there's one element in the queue, but that's not the element that's supposed to be there. It's supposed to have 2. So that's a problem. But if I add something else on, what do I get? Oh look, now I see 2, but I don't see 3. Let's add something else. Now I see 2 and 3. You should start thinking at this point, maybe my indexes are out by 1. So maybe the first isn't actually pointing to the first element in the queue. Well, let's add something else. Oh dear. And I run out of space as well. So I fall out the end of the array. Because I compiled this with DCC, I get some nice error messages, and it actually tells me that queue last has the value 4, and I know that the array had 4 items in, so the valid indexes are 0 to 3. So I've just incremented, fallen off the end. So all that information here helps you to kind of work out what went wrong. And what went wrong was the position of last, and also the position, well, first was actually in the right position, but last was incremented inappropriately at one point, and it didn't wrap around like it was supposed to at another point. So there's actually 2 bugs that need fixing here. I've got a version where I fixed one of the bugs. So this one, and then if I go dequeue, takes it off the front, dequeue again, takes it off the front. Yeah, I can add one more. So I can add one more thing on the queue. I can dequeue will take the front, dequeue will take the front. Now I've got an empty queue. If I then try to add something else, let's add 11. Oh, it works. Oh, this one must be correct. Oops, didn't think I'd fixed it that much. Add 5, no, it's not correct. Alright, I thought I'd reached the end already. So this has got the same problem. That last ends up with a value of 4, where 4 is not a valid index into the array. Alright, so the problem with that is the fact that we're not wrapping around. So if we go back to here, we're simply incrementing first, and first is going to go from 0 to 1 to 2 to 3 to 4 to 5. It's never going to go back to the start. So we want to have some kind of way of making sure that when we reach the maximum value, we go back to 0. And the way to do that is just to use mod, which if you were looking carefully, you would have seen it down here. So this is actually the thing that we need to do for wrapping. Alright, so we just increment and then take mod of max. So if Q first goes from 3 to 4, then 4 mod 4 is 0, so we go back to the start. So it's okay for first to be equal to 0, 1, 2, 3. When it reaches 4, mod 4 goes back to 0. And of course, 1 mod 4 is still 1, 2 mod 4 is still 2, 3 mod 4 is still 3, but 4 mod 4 takes us back to the start of the array. And we've obviously got a similar kind of thing going on here, where that's just incrementing without worrying about reaching the end of the array. So that's also a problem. Alright, so we can fix that and write it out. Star's gone away, so we're about to compile the correct version. And the reason you would have noticed before that it didn't recompile, even though I changed the file, was Make just said Q1 is up to date, when I had clearly made some changes to the QArray.c file, I just hadn't written them out. So QArray.c was still the old version, and Make at least recognises that. Alright, so let's see if we have any luck this time. At 2, oh dear, still got a problem. Okay, so we've got this problem is still there. So we wrapped all right. And of course, if I try to add anything else, it should complain because the array is now full, the size is 4, and it'll tell me Q overflow. Alright, so the only issue is this thing here, which if you go and look at the show function, the thing that's displaying the Q, it starts from position first and goes through n times, where n is the size of the Q, and if it needs to wrap around, it'll wrap around. So clearly that first value is not correct. It's first has jumped along to the second position and installed the new value there. So let's take a look at the code. Right, well, there can't be anything wrong with that line of code. Why isn't it highlighting? So we obviously need to increment the size. If we've added something new to the array, we need to store the item in the array. We also need to increment last, except in the scenario where the size is equal to 0. So remember that we had a special case for the empty list when we were dealing with linked lists. Here we've kind of got a special case when the size of the Q is 0. So Q, oh dear. So I've lost my code. I will get my code back. was network, wasn't it? Thank you, UNSW, for providing such wonderful network service. This is being recorded. Oh no, and I haven't got a copy on my local machine, so I can't just switch to there. Alright, while that's spinning around endlessly, let me try to do something here. I know what I can do while we wait. I'll come back to queues. The other thing I wanted to talk about today was the C compiler. Oh, and I can't even show you the notes. Oh no, what a debacle. Alright. Anyway, so the C compiler is either called GCC or DCC. DCC is actually a Python script that Andrew wrote, which invokes the C compiler and reads what happens when you run the program and produces useful error messages. So the ones that we saw before, where it was displaying stuff in red. So that's coming out of the Python script. So it runs the program, grabs any error output that comes out, and then converts it into a form that's readable. It also, if you noticed, it displayed the values of some of the variables, so it's actually using GDB to do that. In any case, so the C compiler takes a .c file, and the first thing it does, it doesn't compile it, it runs it through the preprocessor, which basically just changes the text of the program in a number of interesting ways. And I had some examples set up, but I reckon I can set them up again on here. Let me see. Oh, that's pretty big. Not too big. There we go. Right. I'll just start faking my week 11 directory. That thing hasn't ever come back, has it? Is that beach ball still spinning somewhere? Could be. Who knows? Yep. Right. So here I'll just write a very, very small program. Won't even bother with command line arguments for the main program. And here I will define an array. And maybe I'll right, if I want to, I can run that program through the C preprocessor and display what the C preprocessor does to the code using GCC -e. Oh, might want to write that out. Or DCC -e would work as well, but since DCC is a Python script that only exists on the CC machine, so I'm running things locally on my Mac, I can't use it. Alright, so there's the command that I ran, and here's what the preprocessor produces. One thing to notice, that hash define has gone away, and where I had a max in the program, I've now got A10. Okay, so that's what a hash define does. It basically says, wherever you see max in the program, put the number 10. Why do we do that? Why don't we just write the number 10? Because we want something meaningful, a meaningful name. Now max isn't a particularly meaningful name. Could have used a number of elements or something like that. Would be slightly more meaningful. Yeah, thanks. So anyway, the C preprocessor basically just takes the C code and makes some transformations to it and gives you some more C code. Now, one thing that you may notice, it's pretty obvious, is you've got all this stuff at the top. Those hashes are going to be ignored by the C compiler, so all that stuff is effectively treated as a comment. And so the critical thing that happened was that caused that to be replaced by 10. So that was all. And if I edited this and I put some other places, if I use max in other contexts, let's int. So once again, everywhere that I've used max, it's just replaced by the number 10. Okay? So that's one kind of transformation that the C compiler can do. Another kind of transformation, that the C preprocessor can do. Another kind of transformation that it can do is something that we briefly looked at before, but let's say, for the sake of argument, that I don't want this int I equals max to appear unless I'm debugging. And I'm going to indicate that by defining a name debug, and only if that name is defined is int I equals max going to appear in the program. Now, nowhere up here is debug defined, and so when I run the C preprocessor, that statement about I equals max goes away. So it doesn't appear in the final result. If I wanted to, I could add a hash define at the top and not debug. And it actually doesn't matter what you put here. You could even leave that empty as long as you hash define debug. Then when it gets here, it's going to say, debug is defined. Therefore, I will include this piece of code in the final output. Oops. Okay, so now we get int I equals 10 comes back. All right, so that's kind of useful for having code that you sometimes want to appear in the program and sometimes you don't, especially if you've got a whole lot of debugging code that you've put through your program and you eventually want to compile a program without any of that debugging code. If you wrap the debugging code in things like that, then it's really easy to get rid of it. Another way, if you really just want to get rid of something, comment out a big slab of code, you can just say hash if 0, and that effectively comments out everything up to the hash end if. So I think I might have done that once or twice as well. And you can see that the syntax highlighter has recognised what I'm doing and it's made it all blue, which is the syntax colour it uses for comments. So if I ran that through the C compiler, then all I'm going to see is int A max, printf, hello. That won't appear. If I did that, then it would appear. Okay? So effectively it's treating this thing kind of like a Boolean expression. 0 means false, 1 or some non-zero value means true. Now if I went back to the original version that I had, if def debug, might be a bit tedious to put the hash define debug yes in your code, and you can actually do it from the command line. So you can go gcc minus capital D and then the name of the symbol that you want to define, and then minus C and x.c. So that effectively compiles x.c but with debug as a defined symbol. So when I get to that if def debug, then the code that follows that is going to appear in the output. So we should see int I equals 10 appearing. So that's kind of useful, and you'll find this quite frequently used in makefiles. So you set that -d flag if you want the program to be compiled up with all the debugging output, and you don't set that if you don't. Alright, so that's the preprocessor. No, I haven't quite finished with the preprocessor. The other thing that the preprocessor can do is do things that look like functions. So I could define something like that, and whenever the C preprocessor sees inc followed by something, it's going to substitute that in the output by putting something equals something plus 1. Okay, so down here I could write don't need that. Don't need that. Alright, so let's see what that does. Now obviously it's easier to write I++ in that context. I don't remember whether I wrote that out. Okay, so you can see where I had inc I in the code, now I've got I equals I plus 1. That's occasionally useful, but you need to be a little bit careful about it, because it will let you do things like, that's perfectly valid. So what that's going to turn into in the output code is I plus 2 equals I plus 2 plus 1, which isn't actually that useful. So anyway, just show you. Okay, so that's going to produce some invalid C. So you need to be a little bit careful using those kind of hash defines, but they can occasionally be useful. Where's the context? Oh, if we're chaining along a linked list, you know how we always have to do code. Then you can do something, you can define. And then rather than writing current equals current next, you can write mock current. No, you can write move current. So marginally shorter might make sense in some contexts, but let's just look. Oh, and interesting, let's see what happens with inc as well. Okay, so this one was the one that I wrote directly into the code. This one was produced from the hash define of move. Okay, so potentially useful. The other thing to notice that the inc, because I don't have a hash define for inc, it just leaves it as is, and the C compiler is going to see that and think that somewhere you've got a function called inc. Okay? So there's no transformation that happens there, but this was produced by a transformation because of the move hash define. Alright, well, let's have a break there, and hopefully the network will come back and we can get back to debugging queues after the break.